Okay, welcome back. Let's continue with support vector machine example. And so I would want to emphasize that, again, we are given data that was not linearly separable, and we transform them into a feature space using a function, okay, of phi that makes our data now linearly separable. So what we did was previously okay, this one. Previously, it was in this form. This is the input space. And so there's no way we can draw a line. Okay. So we draw a line to separate the data. So we introduce a transformation function that will transform the input data into the feature space, the input space into the feature space. And what this function does is that for data, that is because here, this is the norm of the data here is less than 1. I mean, it's 1 or lower, because here the norm is 1, or no, square root of 1, or 1, yes. Yeah, the norm is 1. And so what the function does is that if the norm is greater than 2, then you transform. So now, so here, this is 2. I mean, this is 2. The norm is greater than 2, I mean 2 or more. And so here it becomes now, with this function, the data now is transformed into this quadrant, okay, into this positive quadrant, where they are just like then thrown there now. And then by doing that, we can now we now see that these are the support vectors for the red box, red squares, and support vector for the blue diamonds. Now, in this case, we can linearly separate them. Okay, so using the linear separation, we found out that our W has to be in this value, W1 and W11, and B is -3. Okay, but then we say that we have to apply this classification in the feature space. Okay, now, any questions there? So now we are going to classify any given data. Okay, from here, this is how we are going to classify any given data. From the input, okay, given, okay, this is the function that will f of x that will classify whether +1 or -1. Remember, this is equal to y, which is the classification, +1 or -1 in our case. So the f of x classification now is of this form, where you transform your input x into the feature space, okay, multiplied by the transformation of the support vector into the feature space, and then multiplied by the alpha that we computed. That alpha that we computed in the feature space as well. Okay, and then whatever the result here, your sigma z, it will be just the sign of whatever is inside. So if the sign, okay, sign meaning if it's greater than 0, greater than or equal to 0, that's a 1. Okay, if it's less than 0, that's a -1. Okay, this sigma is just a sign function. Okay, for example, so now we classify a 0.45. So where is the 0.45? This one. Okay, well, this is our initial input space. So that means that somewhere here 4 and then 5 up there. So we want to get that 1 point and classify it. Okay, so what will be the classification? Most likely it will be, will it be a positive or a negative classification? -1 or +1? What do you think, Linyatsu? What do you think? With the 4, 5. So it will be +1. Okay? Because you remember, these outside the blue diamonds are +1 classification. The red boxes or the red squares are -1 classification. So the 4, 5 is somewhere here. So it will be +1. Okay, let's check if it will be a +1. Okay, now, oh, it's not +1. It's a -1. Okay, so now for 5. So x is 4, 5. So now we transform them into the feature space. So if you transform 1, 1, we know the result of this one. It will be just 1, 1. Okay, because this is according to our function. Again, with this transformation, function only transforms those data points that are with a norm greater than 2. Okay, so if the norm is less than 1, so it remains the same. Okay, so here the norm is greater than 2. So what is this now? So let's try it again. So our function is like, okay, our function of x, okay, where your, in this case, your x1 will be 4 minus x2, I think. Okay, plus x1 minus x2, absolute value. And the second component, 4 minus x1 plus x1 minus x2. Okay, there. That's how we transform it. Okay, now let's transform this 4, 5. So what is 4, 5? So 4 minus 5. Okay, that's a 1. Okay, that's a 1, absolute value. So that's 1 and 1 here. So 4, x2 is 5, yeah? So 5, 4 minus 5, that's a -1, so that's 0. So -1 plus 1, so that's a 0. There, that's a 0. So the next one, x1 is 4. So 4 minus 4, that's a 0 plus 1, that's 1. So there, it's 1. And then the bias, we put the bias 1, 1. Okay? Again, why do we put the bias after we transform them into the feature space? Why? Jason? Why do we put the bias after we transform, not before we transform them? Why do we have to do it after we transform? Jason. Remember, okay, just to make it fast because we're running out of time. Remember that we do our linear classification into the feature space. Okay, the linear equation of W transpose times X plus the bias B applies to the feature space because that's where we are going to linearly separate the data. So that's why we put the bias in the feature space. Okay, we transform first into the feature space, the input data, we transform into the feature space, then we apply the bias. Okay, because all those alphas and the weights that we are going to use are in the feature space. So now this is 1, 1, including these alphas that we use are from the feature space. Okay, so multiplied by alpha, and this one multiplied by another alpha, alpha 2. Again, we transform this. What is this now? This is the second vector, support vector. That's a 2, 2, and the input of 4, 5. So this is 2, 2. So 2, 2 remains the same also. We have seen it. It will remain, it will become 2, 2 also. And then now it will not change. We have seen it. And so the bias is 1. And so in the case of 4, 5, again, 0 and 1 and 1. Okay. So when we complete this equation, we substitute and compute, it's a -2. So the sign is what? The sign is -1. Okay, so that's answer. That's the classification. Okay, so what does it mean? How come there's a -1 on the outside?
No, in the inside.
No, this is 4, 5. This is 4, 5. This is outside. 4, 5, that's outside. There. 4 is here.
Okay.
And 5 is here. There. That's the point. This should be a blue diamond. Hold on. Okay, 4 here and 5. And we write a blue diamond so that it will look nice. Let's make it big, make it a little bit, higher carat. There's the blue diamond. Okay, it's there. And the classification of this is -1. Okay, so that means it is not a blue diamond. It is a red square. So this is not a blue diamond. It's a red square. So it means that our classification, our feature space is not correct. Is that it does not classify them correctly, because we are assuming in our feature space transformation is that everything outside of this circle are all blue diamonds, but it's not true. In this case, it's saying that that's the red squares. Now these are blue diamonds, and then another circle will be red squares. Another circle will be blue diamonds, like that. If we keep on trying, maybe, I'm just guessing that maybe it will be like this. But what is saying that based on our computation, there is a red square here. And so our feature transformation was not enough. Okay, so let's try another one. Let's try another transformation. Okay, they call it a kernel trick. The second, this is classifying SVM using what they call a kernel trick. Okay, so the problem here is that somehow there is, okay, in this case here, it is not like that. I'm saying is that my theory was that there is like this, and there is like that classification, because here it becomes negative. Okay, there is like that. That was my theory, that because here it becomes -1. I don't know what's the value here, but anyway, what the author is saying is that in that case there is a different classification. Somehow it splits into this. Okay, it branches like that. So that means that somewhere here it branches also like this, and it branches like that. The data branches like that. We don't have a control over those information. Okay, that is just how the data is. All we can do is just classify them. So if that is the data, how do we classify them? Okay, that means that here there are red squares here, red squares. Okay, here also there are red squares like that. That is their theory. That is the case. Maybe that is really the case. I don't have time to check. Let's just accept it. And then there is the blue diamonds are here. There. That is what the author is saying. Okay, this is how the data is distributed. So if that is the distribution of the data, our previous approach does not work all the time. So now we need to change our approach. So how do we change our approach? So we introduce something like a kernel trick. Okay, our first sigma, our first phi function, preserve the number of dimensions. That means the input space, the output space becomes the input. Okay, in our previous phi, the input x1, x2, okay, outputs another x1, okay, let's just say tilde, okay, x2, another value, but then the dimension remains the same. Okay, that means this is 2D input. The output becomes 2D also. So what the kernel trick is doing is that now we increase the dimension of the feature space. Instead of 2-dimensional, it becomes 3-dimensional feature space. You understand? So most likely it's like for example, you see an aerial view. Okay, you see people, all ants only. Okay, And then you cannot really, you can only see that one from the top. But if you see on the side, there are more features that you can see. Okay, so the same thing, that if you consider only the top view, maybe you limit yourself to certain information. But if you move into the different dimension, if you increase the dimension and now you look at an additional dimension, then you will see that yes, there will be there are additional information that you didn't previously see, that now will help you in terms of classification. Okay, so that's the kernel trick. We make the input space into, we make the effectively, okay, let's just read it. Effectively, to separate the data, the feature space is of higher dimension than the input space. Okay, now what is the third dimension? Okay, previously this is the two dimensions, x1 and x2. Now create a third dimension in this term. Okay, how they come out with that term? Okay, I'm thinking that this is empirically formulated, that most likely this is what it is, for convenience as well of computation, for other things. But anyway, there is that third dimension. Okay, so now this is our second function, transformation function. We transform from 2D space into 3D, from 2D input space into a 3D feature space. Okay?
So,
yes.
If we transform into a 3D space, does that mean now the points will need to be separated by a plane instead of a line?
Okay, that's a good question. We're always saying that although it looks like a line, linearly separable, is separated by a line, we always say it is a hyperplane. Okay, that hyperplane, that line, if you look at it from the side, it is a hyperplane. Okay, if you look at it from the top, it has always been a hyperplane.
Okay.
Okay, it will take care of that space. Yeah, that's a good question. Okay, but yes, they're still separated by a line, by a straight line, if you look at it from the top. Okay?
Okay.
Okay, let's move on. So now this is your transfer. I guess you know already the exercise that we just have to input like this and we transform it into a feature space when we apply the same equation. So now this is your kernel trick. Okay. This is your the second transformation function. So your input data here with now into the feature space. So from the original input space, now we transform them into, we'll just substitute. So substitute x1, x2. So x1, x2. Okay, this was the previous information of that phi1. This was phi1. Okay, for if you do input space, this was the phi1. Okay, I think this should have been, let me memorize it. This part, this is the one that 2, 2, 2, minus 2, then all negative, and then positive here. So all 2, but positive, negative, negative, positive. Okay, so it should be all 2, okay, positive, negative, negative, positive. So all 2, okay. So that's a 2, 2. Okay. Okay, I'm just looking at it from the original input space, 2, 2, and this is minus 2, minus 2. And this is minus 2, 2. And 2, minus 2. Okay. Okay. The other one is this one. It didn't change before because this was the phi that we were using, the phi1 that we were using. Okay. Anyway, it should have been this one remains the same, and this one is the one that was transformed. So now let's go back to the original input space. Now this is the input space value. And so we put this one inside this kernel trick. And so now the first, all the top portion will be the same. So that will be the same as that because You see the function is like this. Okay, just copy x1 and x2. So the top portion here will be the same. Okay, you see that? Now the bottom part is the one that will change. So in this case here, so this is 2 squared plus 2 squared, that's 4. Always 4 because this is positive. You square everything, so that's 4 no matter the signs are. So 4 minus 1, that's a negative 1. Is correct? Sorry. 2 squared is 4 plus 2 squared is 4. So 8 minus 5. Okay, what is that? It's a 3. Divided by 3, that's a 1. So everything is 1. So here at the bottom here is that this is 1 squared plus 1 squared. Okay, so 1 plus 1, that's 2 minus 5, that's minus 3. So minus 3 divided by 3. So always negative 1. So all negative 1. There. That is your feature space now. Okay. So support vectors, they say all of these are all support vectors. Let's just say. Now let's compute. Okay. Okay. So we copy the same thing. Okay. Alpha of up to how many you have support vectors. You have 4 support vectors. Okay. 1 to 4. Okay. You have alpha of all the information, theta 1, sorry. You have support vector 1, okay, multiplied by theta 2 of support vector 1 to 4. What does it mean? And then alpha 2 times support vector of 2 times this one, support vector 1 to 2. Okay. I cannot remember now why this index is 1 to 4. Okay. And this index is 1 to 8. I remember, I know 1 to 8 because these are all the data points. Okay. Okay. They were saying that all the okay, because here you say all the points are all support vectors. All vectors are support vectors. Why? Because you see there are 8 points. Okay, there are 8 points, and we are saying that all the red dots here, okay, when we transform them into the 3D space, okay, we'll have, how come so many people are calling? Hello? Hello?
Hello.
Yes.
Yes, Prof.
Yes.
How are you?
Sorry, I have a class.
You have a class?
Yes. Can you call me later?
When can I call you? But this is very early. You can't step out of the class.
No, I'm in online having a class.
Oh, you're online on class?
Yes, yes.
How long?
Around 30 minutes.
Okay, thank you very much.
Yeah, bye. Okay. Now we are saying that okay. So all of them are we are saying that all of them are support vectors. So okay, maybe yeah, but anyway, you consider them all the support vectors in terms of how we transform them. Because you see, when you transform them, this is in the 3rd dimensional space. This is a positive one, so it just goes up. Okay, in the 3 dimension, this one goes up. Where's the positive ones? Are the ones inside positive, or the ones outside are positive, right? The blue diamonds are positive, right? The blue diamonds are positive. So if you transform them into 3-dimensional space, okay, transform them into 3-dimensional space. Where is that? Okay, here. So this one becomes, this is positive 1 and positive 1, positive 1 and positive 1. Okay, so that means if you see it in 3-dimensional space, then all your blue diamonds are on top. Okay, and then now this is your three-dimensional space. Two diamonds on top, and then the red dots are at the bottom. Here, the red squares are at the bottom. You understand? Okay, but no matter in this configuration, they remain support vectors because clearly they remain as boundaries between the two data sets. Okay, anyway, we consider all of these as support vectors. Okay, and so now we have to compute them exactly the way we compute using the alphas. Alphas times the support vector. So now we have 8 support vectors, 8 support vectors multiplied by the classification. Okay, so now this is the question. So of all the 8 support vectors, so now why do you consider 1 to 4 only? One to four only. Because, okay, remember here, look at this one. These blue diamonds are the positive classifications. These are the positive classifications. Okay, so we consider only those as support vectors. There are 4 of them, S1 to S4. Okay, so that means that you have all these equations for S1, another repeat the same equation for S2, repeat the same equation for S3, repeat the same equation for S4 with a positive classification. We do the same thing from S1 to S4 to S8 because there are 8 support vectors. Now, for the negative classification, you do it for S5 to S8. So we repeat this. You do this equation for S5, then repeat for S6, repeat for S7, repeat for S8 because those are the negative classifications. Okay, but if you take one of them, okay, now you have 8. Okay, you repeat this for S1. Okay. For S1, this is the value. For S2, that is this equation here. For all the positive classification, you have S1, S2, S3, and S4. So S1, S2, S3, and S4. For the negative classification, you do the same thing for S5, S6, S7, and S8. You remember? Now you understand? Okay? Okay. Anyway, the matrix is an 8 by 8 matrix and it is invertible. So now you can solve for your alphas. So the answer is that your alpha, okay, for alpha, for negative, for positive classification is 1/3. For alpha of negative classification is -2/3. Okay, so now if you compute this alpha with respect to the S1 value, now you have 0, 0, 4. And so that means that your X1 and X2 is 0, and then it is the third value, the B value, that makes the classification. So that the discriminating factor is the X3. That means it is the third component of this equation. Okay, so how? So that means that all we need to do is, this is the feature space now. So this is the classification. So all we need to do is compute for the X3, and then that's it. You will know whether it's positive or negative classification. You take the sign of the third component, and then you know that it is positive or negative. That's it. Any questions? Okay, let me recap. In this case here, the kernel trick gives us gives us a method that will take care of making more accurate classification in terms of increasing the dimension of the feature space. And in the most part, this kernel trick works. Okay? In some cases, the first trick that we do, the other trick that we do, the transformation function that we do was not, it was a function on the same dimension. So it was not true all the time. So now we do a kernel trick by saying we add an additional information, an additional dimension that will take care in this case of the missing information. And so with this additional information, we were able to now identify the new alphas, okay, the new value of the alphas for all the eight support vectors, because in this case all 8 of them were support vectors. And so we made these equations for the positive classification. That means for the positive classification, that's S1, S2, S3, and S4. Okay. For the negative classification, you have S1, S5, S6, S7, and S8. Okay. So now these are all the 8 equations. So this we need to repeat. I hope you understand this. This we need to repeat. So this S1, okay. So repeat this one for S1, positive classification. Repeat this, that is the equation. Repeat this one for S2. Just substitute this one with S2, positive classification. Repeat this equation for S3, positive classification. Repeat this equation for S4, positive classification. For the negative classification, you repeat this equation, but negative this one, and so on. And so now you can solve for your alpha that are, because you have 8 support vectors, so you have 8 alphas. So your alphas can be computed with this 8 by 8 matrix. So alpha 1, alpha 2, alpha 3, up to alpha 8. Now we see that this is the alpha. For alpha, for negative classification, that's 1/3. For alpha of the positive classification, that's -2/3. Okay, so now you see here the alpha times S1 up to 8, S8. And so that is alpha for S1, okay, S1 for positive classification, S1 up to S4, that is alpha for positive. So that's 1/3. So for S of 5 to 8 is a negative classification, then that is -2/3. Okay, you get this one. So that means your W is equal to, then the alpha is 1/3 times S1, whatever your S1 is, plus 1/3 of S2 plus 1/3 of S3, because those are all positive classification, up to S4 plus 1/3 of S4. Okay, now you're going to the negative support vectors. Okay, the negative classification. So -2/3. Okay, S5. Okay, -2/3. S6. -2/3. S7. And -2/3. S8. Okay, there. Then you can solve for your W. And so in this case here, the W is 0, 0, 1. So the weights, in this case, your weights that will classify your values of the function, the linear classification, is x1 times 0 plus x2 times 0, okay, plus 4 is equal to the classification f of x, or equal to y. So all that matters is actually the third component. So whatever is your third component, whatever is your bias, okay, your input will be, because the third component is consisting of what? What is your third component? The W, that is your bias, and your third component is what? X, what is that? X1 squared Okay, let me write it down because these seem to be okay. Here, okay, the third, we know already how to compute the weights. So in this case here, you have W1, W2, W3, okay, transpose multiplied by your X1, X2, X1 squared. Remember, that's your third component, plus X2 squared, okay, minus 5 divided by 3. That's it. There. This is your Y. Okay? So now, because this is 0, 0, 4, okay, multiplied by this one, so that means this does not matter. So only the third component of your X matters. So we check only the third component of the X, which is this one, say, and get the sign, or whatever the sign is. If it's positive, that is positive classification. If it's negative number, it's a negative classification. Greater than or equal to 0 is positive, less than 0 is negative. Any questions? So with the kernel trick, okay, it's a little bit more complicated in terms of computing the alphas. And now you have more support vectors to consider compared to the other case where you only have 2 support vectors. It's easier in terms of computation. But now this computation of the alphas are a little bit more complicated. But eventually, in terms of classification, it turns out to be an easy classification. You only need to consider the third component. Then you can classify your data to be positive or negative classification. Okay? Okay, that's it. And then now, I guess everything is clear now. I will give you the exercise for support vector machine. And then the deadline is next week, just before lab time. Tomorrow, I will start discussing neural network. And then next week, I will finish neural network for the 2 days, and then you will be ready for the long test 2.